webinar series on data science for environmental sciences, and it's my pleasure to have Frederik today, and I'll give the floor to you, Juchen, who is the host. Thank you.
Okay, so hello everyone. So thank you all for coming and joining us to our webinar today. And this session consists of 40 to 45 minutes presentation and 10 to 15 minutes for questions and answers. So I'm very honored today to introduce our speaker, Dr. Frederik. And Dr. Simons is a professor and associate department chair of the Department of Geoscience at Princeton University, and also associate faculty of the Princeton Environmental Institute and associate faculty of the program in Applied and Computational Mathematics. So in addition to his more than 15 years at the Princeton University, so Dr. Simons had visiting professors and fellows appointments at a number of other universities, including the IPGP France, ETH Zurich, Switzerland, KU Leuven, Belgium, University College London, UCL, and so on. And Dr. Simons is also a former member of the Institute for the Advanced Study IAS. So his research interests encompass various aspects of the solid earth geophysics, including the seismic, mechanical, thermal, and magnetic properties of the earth, lithosphere, and the terrestrial planet and the moons. And more specifically, Dr. Simons studied the physical properties of the terrestrial lithosphere, focusing particularly on the elastic and the thermomechanical properties of the continent. So again, so I would ask you all of you, please join me to welcome Dr. Simons for his talk today, Beyond the Roughness, Efficient Parameter Estimation of the Sampled Random Fields in Geology and Geophysics. So Dr. Simons, the floor is yours.
Thank you very much, Joe. I'm going to go full screen, and that means that I won't be able to see all of you very clearly. But I'm going to try my best to keep some notion of who's at least one face here. I think you do see all of that, and I need to hide you a little bit. So please, I'm not seeing you, so if you guys want to interrupt, just please do. It's much more fun if it's that way. I also, I think none of you are geoscientists, and so I'm going to go light on that. I'm going to give you plenty of motivation, and I think since you're a new crowd for me, I don't know exactly what to expect, so but please feel free to interrupt me, because otherwise it's going to be boring. So my two collaborators on the first line are Gabe Eggers and Kevin Lewis, and they're geoscientists, postdocs and students that work with me. And Gabe is now at the Lunar and Planetary Institute, and Kevin is at Johns Hopkins. Most of this, well, all of the statistics really that I know, I learned from Professor Sophia Olhead, who at the time was at University of College London when I was there also, but since has moved to EPFL in Lausanne. And then her postdoc, Adam Sikulski, who is now on the faculty at the University of Lancaster. And then their grad student and now postdoc and now lecturer at Queen Mary, University of London, and that's Arthur Guillaumin, whose paper is just about to come out. And so that this reflects a very long, in fact, collaboration. I think we started almost 10, 12, 13 years ago, coming on the same page in defining what our problems are and then making progress, fast and slow as those things are going. So the title of our paper that's about to come out is the de-biased spatial Whittle likelihood, and I'll be defining it. And the goal here is to go and do efficient parameter estimation of sampled random fields in geology and geophysics. And I'll define all those terms for you, but I'll just get into it. So in the big picture,
Professor Simons, sorry to
yes,
interrupt
go
you.
ahead.
So I think there is a find option in the top right part. Yeah. Okay, looks now. Wait now.
So
thank you.
Thank you. So in the first paper, Sophia and I wrote together was in 2013, and we looked at the multivariate problem in geophysics that attempted to explain the linkages between topography and gravity, and that there's a lot of physics inside of this coupling that I will not talk about. So I'm going to go univariate here for you. And what you have to imagine is that we are planetary geoscientists, and so we look at things on a planetary scale. So here's a picture of the globe. You recognize our continents, you recognize our oceans, you recognize that the variations of elevation are containing lots of structure. They are non-stationary random fields. They are of a varying degree of roughness, however that's defined, and I want to go beyond some traditional notions used in our field. There is structure, there is anisotropy. I imagine none of you look at this very often, and actually I'm going to try to point with this pointer here, right? So you see these stripes, those are big fracture zones. You see Hawaii, you see volcanic change, you see the big Rocky Mountains, you see the Andes, all sorts of things. So how do we characterize that? What do we do with it? What does it all mean? That's really the central question that we have. And I think that's a general question in environmental statistics. Application here is planetary topography. Can we find a law for it? And if we have a law in a parameterized way, can we find the parameters? And can we find how well we know them? And can we judge whether that's good enough or whether the model even applies? And then really where I'm going to need to end as a geoscientist is what do these parameters really mean? How do they evolve? How do they co-evolve? So here's another planet. If I could see your eyes, I'd see if you recognize it. I'll just tell you now, but this is Venus. So the surface of Venus doesn't look anything like the Earth. How do we tell that if we don't know a process level? If we don't have a process level understanding, can we see that through those parameters? Here's yet another planet. This is the planet Mars. Its surface, once again, doesn't look anything like Earth, not in its geology, not in its geophysics, and not in its statistical structure, presumably either. And finally, here's the moon, yet again, completely different. And of course, you know about the moon, it's a heavily cratered surface. And so that's just one aspect in which this planetary field differs from all the others. And so in large scale comparative planetology, if you will, we are really trying to learn from these surfaces and from the fields associated with it, like the gravity and the magnetic field, what the structure and evolution of these bodies are. And here I'm going to try and use this as the coat hanger to hang the fact that we want to do efficient parameter estimation of pieces of these fields to learn their differences and to infer what sort of things are going on. Now, oops. When I said sampling, I do want to give you two ideas. When we think about the depth of the oceans, and I just plotted it a few slides ago, that's really not a direct measurement of thing. That's a model made from some direct, some indirect measurements. Indirect is from satellite data that incidentally measure gravity in order to infer topography, which is another story. And directly because, ships do soundings. This is an older slide, but, in 1997, when the big global model that many of us still use, although it's got many refinements, was published, they also published this map here of, the direct ship track measurements. And so you're seeing that there's a lot of missing samples, just the oceans, right? We do it another way on the continents. But you're seeing a lack of sampling in the southern oceans. You're seeing structured samples because this means that ships are going on trajectories. And yet we have to make a model for it and we have to do inference on it. And there is a very heterogeneous type of sampling behind many, many of the fields that we all look at. Here's another extreme example or it's a very common example that shows how extreme the common case is. This is for those of us studying ice structure. This is a piece of Antarctica, and it's showing the various types of samplings that went into making a particular model of the ice sheet and the bedrock below it. And so you're seeing a combination, again, of tracks from a central point. You're seeing, larger grids, you're seeing finer grids, you're seeing individual curves, and you're seeing all sort of heterogeneity. And all of that, ultimately, we need to stay as close to when we're doing model inference, and yet be as little influenced by it, so that we don't map our sampling onto our inference and fill in the gaps in the right way and do the learning in the right way. So the statistical research objectives then are, we have a lot of samples. I know you all do too, but so when I say we, is, planetary science, geology, geophysics, that's tens and tens of thousands of samples, large fields. Second of all, our areas of interest are irregular. You notice the continents are different from the oceans. Belgium, Michigan, they have weird boundaries. And we have grids underlying them that would lead to boundary effects and aliasing. So finite field effects. Even if we have regular grids, we have missing data that we want to efficiently be able to treat. And then we have these extremely heterogeneous and structured sampling patterns that could be points and lines and curves and grids that here in this talk, we're not at all solving all of that, but we need to be aware of and work towards dealing with efficiently. So the underlying process, I'm going to talk about Gaussian processes. We do also have to think about non-Gaussian, and we are extending some of our theory to that. And then I mentioned that much of what we're actually doing is multivariate, but right now I'm going to be univariate because it's already enough. So then the last point here is on this word efficient, and I'll explain it again later, but Fourier-based methods for estimation of covariance structures are attractive if you can do n log n operations, if you can do fast Fourier transform. And so we are really liking the Whittle likelihood, which I'll be defining, to do this estimation. And yet none of that works very well for finite fields and boundary fields and for all the complications that I'm showing here. And so we're going to fix that. And that's the notion of the word de-biased. We're going to undo some of the known bad effects of Fourier-based methods to remove bias from boundary effects, from finite fields, from sampling effects, and yet to maintain the attractive efficiency, the attractive computational efficiency, and the statistical consistency of the estimators that we build. So I'm going to just write a few equations to familiarize you with our notation and our general framework here. So I'm thinking of obviously non-stationary fields, but in certain areas and from place to place, we can locally do stationary fields. And that, of course, that comes at the price of defining a boundary and saying, well, I'm going to study, Michigan or Australia. And then we have an implicit local domain. So X is a spatial variable, and we're treating the field in 2 dimensions. So everything that's bold is a vector and leads to 2 integrals in 2 variables. And so there is a notion of a spectral increment process in the sense of equation 1, where h of x is this thing that we actually observe. And so the definition of the power spectral density is the expectation of these coupled spectral increments here. And so that's what I call math cal x, curly s here, s of k, the wave vector, and the under stationarity is really just a k, and so we're getting rid of the coupling between k and k prime in this sense. So it's already very restrictive, but this is where we start. And of course, under 1 and 2, the spatial covariance is just dependent on separation. And so that's my C here, which depends on the distance, sorry, on the separation between x and x prime. And the spatial variance, when I say that, I really am going to mean sigma squared as the covariance at 0 lag. And so that's this constant here. So that's what I'll call the variance. Of course, they're all variances, but that's really sigma squared. Now, if it's isotropy, and much of it isn't, and much of our interest lies in going beyond it, but let's just go to isotropic processes here. Our definition of that is, of course, that it's directionally invariant. And so the S, the power spectral density S, gets this italic K, which is the wave number, which is the length of the bold-faced wave vector. And then we're having this as the thing that we want to know. And then under the same combination here, that means that the covariance in space, our little c here, is dependent on distance only. So that's the norm of the separation vector. And then, of course, the spatial variance that hasn't changed. That's just a pointwise thing here at 0 lag. So I do think you know all of that. And if you're not familiar with the notation, then I think you'll remember H. I think of H as the height of the mountain. So that's our mnemonic for topography. X is space, K is spectral space. Big S or big C are the two properties that we want to know. And of course, they're related via Fourier pair. So we can, of course, never, ever observe a continuous process. And any sampling or any windowing, any of that thing that we do as actual practicing scientists is changing the thing that we want to know. So here in this notation here, I go, well, here, this curly H, it exists as a process. And we are going to map it. We're going to window it. So let's say W is just a kernel of 1s over Belgium, and then that's our boundary. And the straight up, or rather italic, but no longer curly H is now the Fourier transform, the windowed Fourier transform of this sampled area. And that, of course, relates convolutionally to the spectral increment process through big W here, which is this the spectral window, the square of the Fourier transform of the little w. And K is the sample size in most of what I'm going to talk about, but that's big K. So in one line, to show how complicated things are getting due to windowing and sampling, or general windows, little w, is it's really all contained in how the continuous process, spectral density here, this S here that we want to know, gets blurred and correlated. This thing that I said didn't have any interactions between K and just shows us the spectral density as a function of it. When we are actually doing this thing that we're doing, which is an act of measurement, then we're getting this covariance operator between the Fourier coefficients as twice convolved in this way of equation 10 here. And that's what we want to disentangle. So we want to sort of see through how that's going in order to learn from our sampled field what the underlying S is. So quickly, if I ignore it, then, you know, if I ignore the correlation between wave numbers, if I ignore interactions between K and K prime, then I'm going to introduce this thing here, which is S bar, and I'll be referring to that as a blurred spectral density. So ignoring K, K prime interactions, the view of the covariance between those two is going to collapse onto a single wave number, and it will still not be the true spectral density, but it's rather convolutionally blurred again. And that's my definition of S hat here. So I do think you already knew this. Finite fields, right? They always yield blurred and, in fact, correlated spectral estimations. We need to be aware of that. We need to be aware of that when we're doing inference. We need to be aware of that when we're making simulations. And for the purpose of this talk here, we are building that into the definition of our likelihood in a manner that you're going to appreciate in a minute. So until now, S was the thing that we want to know, and we had not parameterized it. Here at this point, I'm just going to say, well, we're using the Matern spectral density, which is a 3-parameter if it's isotropic spectral density, where the 3 parameters, which are not independently resolvable and not in fact orthogonal, are the first one is the variance, the sigma square, which I had defined earlier. Then nu, which is a sort of a mean squared differentiability or a roughness, and rho, which is the range. So that's the 3 parameters we want to know for the various places of geological or geophysical real estate that we're trying to characterize. And we want to know the distribution, and we want to know how to get there, and we want to test for when it's appropriate, and so on. Oops. So just to clear up the last bit of notation here, that same variance sigma square is, of course, the integrated spectrum, and in 1D or in isotropic, in under isotropy, you have this third equivalency here where there's an extra integration k. And then the last thing is that the 0 wave number spectral density is this combination of sigma squared and rho squared, where you're already seeing how those two are being very coupled. So this is also standard. This is straight from a textbook with a slight notational difference between certain authors. And it's a very flexible spectral density. And if you've used it, you'll recognize it. And if you don't, you'll know that it, or you should know, you will know that it encompasses a variety of other known spectral densities as the new parameter collapses onto specific half integers. So you get exponential and double exponential and Whittle and von Karman, and I forget the list, but they're all locking in various known classes. So it's a very flexible hyperclass of spectral densities. So here's some examples. In black is this S of K I've been talking about. The spectral density is a function of wave number. In blue is the C that I've been talking about, which is the correlation, the covariance. And at the bottom are realizations. And the blue circle is sort of a radius of pi rho. So I, just want to give you a feel for the parameters that rho is the distance below which, after which your correlation, the normalized covariance here, goes to about 1/3. You see that happening here, you see that happening here, you see that happening there. Well, in pi rho is, for me, it's a physical quantity, obviously, because I work on real mountains. And so that's about the size of this thing, and that gives us an idea of the interactions. Nu, the parameter nu, is very sensitive to what's happening here and how steeply, or rather a little bit more smoothly, these interactions decay. And even though these are different combinations of sigma, nu, rho here, obviously you know that, well, your eye is not really that sensitive to it. So I'm plotting some specific metrics by which I can draw certain points here. But of course, you'll imagine that if you're doing this in real life, that you'd be getting this, really wiggly estimate of it, and that, the art is in figuring out these parameters. So all of this is all perfect knowledge. None of this is real data. This is purely synthetic. So what do we really do? So in order to estimate theta, the 3 parameters of a field that we observe, we are going to form a log likelihood of observing the Fourier transform data italic H of K wave number under this process that I've just shown you, the Matern process in the 3 parameters. And in this slide, and for the foreseeable future, I'm assuming Gaussianity, and I'm assuming the independence of the wave numbers, which I'm going to return to, but so I'm writing a probability of observing H as a complex normal distribution with 0 mean, and with a variance, which is that blurred spectral density, because again, this is the probability of observing these data when I've actually observed them in a specific region with a specific grid, with a specific boundary. And 17 here is really the key to everything that's happening. And I'll return to it and you might recognize it, but I just want to make sure that you know this is the most important thing, is that the likelihood that we form L bar of the spectral S here in the parameters theta is a wave number average of the log of the blurred spectral density and then the ratio of the periodogram of the data divided by the blurred spectral density, which I'm going to make explicit is really the expected periodogram of the data. And that's the quantity that we will be optimizing, and the theta hat is the best minimum variance unbiased estimate of this parameter vector. And I'm going to talk about the computation. And so that's really 17 is really what we'll be doing for our estimation. And I got to make the argument that this is a good thing and that it's different than what other people are doing and that it's sufficient and all the things that are still coming. So that really does sum up the statistical technique in the sense that if we wrote everything without a bar, we'd be ignoring the boundary and the gridding effects. With the bar, we have those effects which we need to painstakingly characterize. And by building a pseudo or quasi likelihood, an adjustment to the proper Whittle likelihood that takes into account this blurring and finite field effect, we are going to have a thing that isn't solving the real problem, but an approximate problem. And I'm going to tell you how close we are and that it actually does work very well. So that sums it up, right? The de-biased spatial Whittle likelihood is a likelihood like you would get from a Fourier-based Whittle likelihood, but you would, instead of any other modification, you form the product of the observed periodogram and then divided by the expected periodogram under the sampling. Quickly, I'll be talking about things like this. So whenever I say we're doing simulations, then we're making synthetics and we're running optimizations, and we'll always be looking at the three parameters. I'm not going to discuss this in detail right here, but the end of the story is that the estimators we build are good and they are Gaussian, and we are trying to characterize everything we know about them. And that's the type of plots I have in the background when we're doing the estimation, but I'll be giving you more detail. So just two things by which we as practitioners look at the quality of our fit. Well, once we have the answer and the ratio X here is that periodogram to expected periodogram ratio, that's a chi-squared 2/2 variable. That's a very diagnostic number that we use for quality of the fit in general. I'll be talking about the covariance of the estimates more specifically, but this is like one of those tools. And in particular, I use that because we can detect departures from isotropy, which is very important for us. We're still on the null hypothesis that things are isotropic, but we're very interested in building geometric anisotropy into it. And so this statistic here is a quick thing to really see it right away. I'll show it by example. And the next thing is that if you're summing some sort of a fake variance of that parameter X here, that ends up being distributed as a normal with 8/k as the variance. And so that number we actually also use to quickly visually and statistically evaluate if the model is good enough, right? Knowing that we always have the best version of our model, we need to know if what we have then is in principle good enough. And that's those two numbers I use diagnostically to see where that's going when we're looking at real fields. And that's because, that's something I hammer our own students with, right? Like everyone can make a best estimate, but if you start with something that's not very appropriate, you still need to evaluate whether that model is any good at all. So again, I'm just giving you an end result here of saying, well, if you look at these two things, the top line is the behavior of that quadratic residual, that big X, and the bottom line is the behavior of that statistic sigma S squared of X. So I told you the top is a chi-squared 2/2, the bottom is a normal, and yep, in simulations, which my mathematician friends don't have to do because they see it's right away. But when I do it, I always want to have a plot that shows that my computer can do it. And so that's the type of plots that we look at. So this is a test of the test. This is the distribution of the test statistic, which verifies the previous slide. So now here is some synthetics, and this is our dashboard. When we're doing the real analysis, this is sort of the panel that we look at. At the top right would be the spectral density in the Mattern form. At the bottom right would be how it comes out when you're actually doing data. At the bottom left is the X residual, which we want to see as uninteresting white noise. And if we're seeing structure, then the model doesn't really apply and the test statistic will reveal it. The chi-square/2 distribution here, that's actually the distribution of the numbers in the bottom left is shown in this histogram with the modeled distribution, which in this case perfectly fits. This is a pure synthetic. And then the red line is a QQ plot of the values in this plot, and the number S squared over X that I talked about, it, which here I write as the mean of X minus 1 squared. That's the thing that when it's properly normalized, I need to have be a certain value. And so when all of this looks good, we accept our parameter estimates. And so we're looking at this bottom left not having any structure and this red line being very close to a 1-to-1. Here's another example, some more parameters, just to see how, like, of course, you have some real things to see. And I'm making a pedagogical point that when we're having things worked out, I always really want to make sure that we have some really clear visuals by which our eye can do a lot of the diagnostics, so that we're not going in blind, because there is a lot to look at. There is a lot of structure. At the end of this story, or at the end of a run like this, you know, we want to go to a planet like Venus. So I'm bringing the motivation from geology back here for a minute to show, you know, there's all sorts of things going on Venus, and we want to know all sorts of things about it. Let me just give you some more data examples here in the middle of this talk before returning to the statistics, and say, well, look, this is really how we planetarily observe it. This is typically done by a radar mapping. There are definitely missing pieces, and there are left-looking radars and right-looking radars, and they're somehow already combined. So this is really how the planetary science is done, in the sense that, you know, this is the raw data collected by the instrument. And we might be interested in a patch of data that you can tell has some geologic differences from the surroundings. And so when I say a non-stationary field that we treat as stationary, I mean exactly this. We want to have some boundary and say, well, this is what interests us, and within that we're going to make the approximation that, you know, everything works and we'll find its parameter. So that's the radar map. That's just how much of, you know, radar energy is reflected. Oops. This here would be what the topography is. And when you're asking NASA, and you could do this by going to their website and saying, like, give me the topography of Venus, you know, something like this comes out. And again, this is one of those plots that we're making to just look at everything, and then to have some basic diagnostics to see that what we're looking at is you know, of any value. And then when we're doing an analysis, as I haven't properly told you how to do it, we end up with a diagnostic plot like this here, where the top right is the inference. That's what the spectral density is. But you see, it's the you see the window effect in there because that's taken into account. The bottom is how it comes out for this particular patch of data. I've actually contoured the lines. I've contoured the top plot and plotted the contours on the bottom plot, so that if you don't see the contour lines, the model fits the data very well, which is another visual diagnostic. The left is these quadratic residuals, is the ratio of the periodogram value to the expected periodogram value, where we want to see nothing of interest because it should be distributed as the top left. And And the QQ plot would be the red lines. And then whether that is any good is symbolized by this number 1. So this is an example of where, hey, you know, in this particular area of Venus, that Matern model and the way that we find the parameters is very appropriate. It works very well. And so we're going to have some numbers that we can then use in geology to learn something about why it's this way or how it evolved. And I'll spare you that, but that's where we want to go with this. Here's another example. Different area, different contour, different reason for drawing the contour. There's more that goes into that, but let's just say we're interested in the interior of this domain, different topography, different parameters. And this is an example where we flag that there is something still, you know, inappropriate about this model specification. The most important thing that I take away is that the spectral density does show a clear directionality to it, which is very clearly revealed in the residuals, which is very clearly revealed in the fact that this parameter that essentially captures the non, you know, QQ-ness of this red to the black line here, you know, we reject it. So even though we have found parameters for this region through this method, we owe it to ourselves to take a step back and say, well, we must reject this as appropriate because our residuals are not the way we want it. And then that will be the motivation for much further study, because now we have to deal with geometrically deformed spectral densities that are showing anisotropy, which is where we want to go, but we're not there yet. So I want to sum up now the theories in a bit more statistical way, still keeping it relatively light, but I'm going to give you the big ideas of why we did it this way and how we did it, and then I'll be about done. So our data sets are huge. Your data sets are huge. They're getting ever bigger, right? 10,000 points. I just type some zeros. That's nothing. Maximum likelihoods for parametric inference don't scale well. And it's even worse for non-Gaussian data. So we need some things that are workable. Things that are quick, you know, summing and squaring, and it's typically not working well. And we have tried some approaches, but they're known to be bad. Likelihood methods are much better, but you know what we really want is quasi or pseudo likelihoods that are, you know, like the exact ones, but are ideally much faster to compute, so that we can do simulations on huge fields as we need to. The Whittle likelihood is a popular likelihood in the frequency domain, computable using, you know, FFTs and so on, but our problem with that, of course, as I said, is that these standard Whittle-based likelihood estimates are demonstrably bad because of these edge effects, the aliasing of the gridding, the blurring that I described. All of that gets worse and worse with higher dimensional data, and so it's just basically not good. And our central vehicle here is to de-bias that. And in one word, again, we are accounting for the finite field effects by reformulating it. And our paper then shows that it works. And here I'm going to talk about the some aspects of the things that motivated me from the beginning: boundaries and missing data, right? Irregular sampling. And I'll leave the non-Gaussian data out of this here. And the important thing is that we get rid of the bias and we do maintain the consistency, and we have a computational efficiency for large fields. So I'm restating here now briefly something I've said before. Now my W was my window before. I renamed it G here. And so G now, instead of just thinking of capturing the, you know, surrounds of Belgium or something, it's also, it could be a 1-0 switch for missing data. So in this formulation, we're thinking of a grid with an irregular boundary and with irregularly deleted samples. And so that's the boundary and one on-off switch G here, and G over it's so a normalized version of that. So the windowed periodic gram, when I refer to it now, is the square of this here, a Fourier transform dot by dot multiplied by this window and suitably normalized. And straight repeat from what I had before, the central vehicle here is this Whittle likelihood. Sorry, this is the original Whittle likelihood, which would be formulated with the spectral densities, but where we are making this de-biased Whittle likelihood and replacing the spectral density with the barred spectral density, which is S bar is the expected periodogram. And so this is what we do. I know that we're now needing the methods for it, and we're needing the proofs that it always works as well as we say it is. So in the next slide, we need to do a lot of computational detail, right? So because it's one thing to write it and another thing to prove it, and then a third thing it is to compute it. So first thing is that we need an efficiently computable expression for this blurred spectral density. Second thing we'll need is the mathematical guarantees, the statistical guarantees that maximizing or minimizing, depending on my sign here, equation 22, this de-biased likelihood is a reasonable alternative to maximizing the original, which gives us a true answer. So, oops, yeah, exactly. So the paper in GRSSB that's coming out pretty soon here says, well, look, 3 theorems. One is if we do what I just said, we maximize the de-biased Whittle likelihood, we are getting a good estimator with consistent behavior. That's theorem 1. There's 2 lemmas to that. And one of them is that we need an efficient way of calculating this expected periodogram. And we can do this as a Fourier series and or write it as a Fourier series. And then lemma 2 is that we can actually compute it using FFT, which is what gives us the K log K behavior then. And then we show that theorem 1 actually does hold for non-Gaussian and multivariate Gaussian with appropriate corrections, multidimensional random fields. So that's the gory detail of theorem 1. How do we actually compute this? Well, it takes a while longer in the paper, but in essence, if you do some rather direct manipulations of what I showed you before, is then the blurred spectral density ends up to being this here. C, remember, is the spatial covariance, and G, remember, is the grid switch, the boundary selector, and the 1-0 switch on whether you have missing samples or not. And so this thing here is a partially summed lag product, which can be pre-computed for any grid of any size with any missing data via FFT. And you can do it by hand if it's just this unitary window function, because then it's the result of it ends up being a set of triangular functions being multiplied. And so what this means here is that we can compute the blurred spectral density with 2 FFTs, one that we do ahead of time that specifies all the grid properties, and the other one that we may need to do multiple times depending on how we're going through simulation and inversion. So that is the key to the computational efficiency, that the biased Whittle likelihood in formulated with the expected periodogram can be computed really efficiently, and that no matter how complex the grid is, we'd have to do that even once. Then of course, there are conditions on whether this all works, and I want to send you away with a couple more things. And one of them is that the idea of when any of what I've been saying is going to work well, we formulate this in the form of something that we call the significant correlation contribution. And what we require for this sorts of procedure to work the way that we advertise that it does is for there to be, some remaining identifiability as the grid grows. So if we had two different spectral densities with theta 1 and theta 2, and we had a sequence of grids with increasing sizes k, and then the limit of sk of this growing domain asymptotic regime, that we still maintain a diagnostic difference between those blurred spectral densities. So it's more than that, and it's but the essence of it in 26 is that's what we call that we need to have this as an asymptotic condition being satisfied for our procedures to yield those consistent, efficient Gaussian estimators that we have. And that's all proved in the paper. And I am not a mathematician, which means that you're going to have to read the supplementary material of that paper and then have to ask Arthur, Adam, and Sophie about the details of it. But that's the essence of it. Here's a computation, just as a hopefully pretty picture of implementation. Top right is the expected periodogram for a certain sample size of 64 by 64 and a certain set of parameters theta. Top left is one realization. Average over 30 is the bottom right. Ratio over 30 is this. And so, we're really, really carefully vetting our computer code to make sure that there isn't anything remarkable about its behavior. And so, yes, our implementation, which I haven't sold you in detail, but it really is doing what we're saying it is. We are able to compute the expected value of the periodogram and use it to debias the likelihood, and then use it for all the other steps in the procedure. And then theorem 2 and 3 in the paper talk about the convergence rate, which ends up something like this, where you recognize GG normalized again. So this thing that we have pre-computed, squared of the spatial covariance, and without the second term, that's the Gaussian behavior, and then there is a correction term for non-Gaussianity. And when the grid is fully observed and the field is Gaussian, then theta hat is asymptotically normally distributed, which is really good for us and attractive for all of us. And then with some additional assumptions, they maintain this normality even for non-Gaussian fields, and then of course the appropriate corrections. And then the third theorem that we have in the paper is, well, it'd be really nice to be able to pre-compute what the variance of your estimators are in function of the truth before you even started without having to simulate. And so this 28 here is that, yes, we are having forms in which the variance of the estimator relates to the derivative of the debiased Whittle likelihood, and left and right multiply with the inverse of the Fisher matrix. And it's easy for me to write this, and then there's 13 pages to get to this point, and then there is the computational implementation, which is something that we are being very careful about, because otherwise who would ever use it? And so we're sort of at this point where we're done with that. So when push comes to shove, this is the type of thing we want to have, right? We want to have Gaussian estimators. This is an example of how they come out for some tests. Don't worry about the details of the lines, because we have various ways of doing some of the computations, but I think I don't have time for that. Just a quick view of, I mentioned these Whittle parameters are not, independently resolvable. So this is in some estimation of some size here, and you're seeing the trade-off between the variance and the smoothness, and the variance and the range, and the smoothness and the range. But the bottom line is that the computational method works, it's efficient, the estimators are consistent, the estimators are Gaussian, and we could do it for very, very large fields. And then we have some guarantees for multivariate non-Gaussian. This is then the sort of central plot of the paper that shows this consistency. And so you want to take a look at this here, the tapered Whittle, and I'm going to call it yellow, but you should know I'm colorblind, so it may be green, but it's like bright, light colored. And this is bias, standard deviation, and root mean square error. And sorry, well, look at the yellow one and you see how bad it is, right? That is just standard width, but allowing for a window function. And the equivalent that works so much better, this, the tapered de-biased, that's everything that I've been telling you today. So that has effectively de-biased this procedure and maintains 1 over k and 1 over squared k, well, the lines are the ideal behavior here. And so in the standard deviation, we're getting the 1 over squared of k, the k as the length, the size effectively of the grid grows. And so having this behavior for the de-biased version of this width and likelihood is our computational illustration of all the theorems in the paper. And then the last slide here is that, well, take a look at the top left, and it's some actual field. In fact, it is a piece of Venus. And the top right is what we have if we re-simulate after having determined the parameters from the top left using the de-biased whittle. And if we used any of the other more traditional estimates, we'd get the situation is the bottom left and the bottom right. And so this again is a sort of a visual show of how we need to see doing any of this is we have some real piece of planetary topography. We're going to summarize it as some actual numbers that are parameters in the Matern distribution. We're going to learn some physics from it and some landscape evolution and some process geology of it. And then we're going to need to use that for further simulations and numerical modeling in geology and geophysics. And so we have to be able to make realizations from those processes. And then of course our eye needs to be pleased with it, because this is very, very important, is we're still seeing differences, we're still seeing details, and we're still needing to ever adjust our statistical methods to really capture what's going on. But the top two figures, when you squint, you'll see that we're definitely getting right in the right direction of being able to capture planetary topography and having some guarantees that what we know in a fair and in a quantifiable way. So we're still going on as advertised. I'm actually having a postdoc advertising because there's so many geological statistical directions that we could still go. But it's all going to fall under this umbrella that we're for a while are going to continue try to capture the essence of planetary topography or planetary fields in more general as stationary Gaussian Matern fields. And under isotropy, that's 3 parameters: the variance, the differentiability, the smoothness, and the range. We do want to go to anisotropy. It's a very interesting problem and very necessary. In everything we do, we're going to be able to consider finite field effects, which leads to blurring and correlation and all the effects on all of the downstream effects, which we have now appropriate ways to incorporate and correct for. We have a proper simulation procedure. I didn't talk about it, but it also took a while to get to the proper point. And we have an inversion procedure, so by a maximization of this de-biased likelihood. And the estimators are Gaussian, the estimators are consistent. This whole thing seems to be working well. There is lots of things to do, but in essence here, we were already preparing for the next step where we're going to deal with more explicitly with different types of missing data depending on the area of application, and then explore non-Gaussian behavior. And then other means of doing so. And my example here was Venus, and we are mapping that. We are trying to study that. But of course, the solar system is large, and we have many, many, many different fields of interest in planetary geology and geophysics that we want to apply these methods to. So I should stop here and leave the floor or be open to questions.
Okay, thank you very much for the excellent talk, Professor Simmons. So, any questions from audience? Yeah, feel free to ask you any questions.
Thank you. Oh, I have a question. Thank you so much for a fascinating talk. I was going to ask you is how do you consider, for example, water bodies in the Earth versus, for example, other planets where we don't have water bodies? How is that going to be affecting your estimation?
So that's really a geophysical question, right? So of the many things that are important here that perhaps I should begin with, one of them is that when we look at the Earth with water, right? So what I call topography is the height of mountains, and what I call bathymetry is the depth of the oceans. And there we are clearly distinguishing between those because, you know, their surfaces are different. But what you perhaps don't know is that we really always also look at the gravity field, because even when we say the elevation of a certain mountain, it is with respect to a gravitational equipotential. And so really, I think of topography as, like, I rarely can talk about topography without that complementary field of the gravity field, which is very important. And that's why I began by saying we're really always interested in the multivariate problem, and then we know how those things are coupled. But so you have to think about the fact that we can directly observe underwater with, you know, echo sounders on ships. We can also indirectly observe what's happening under the oceans because of the gravitational attraction of, you know, undersea mountains and so on. And so we are able to think away the water is another side product of that, because as you may know, our Earth's sea level has fluctuated by, you know, 100 meters and is currently rising. And so that means that when we look at the Earth that is not underwater right now, that's actually not the full continental topography, because there is a bit of continents that is currently underwater that it used to not to be. And so those are things that we can strip away. And then, of course, on other planets, we don't have water, but on Mars, we have ice, and we have seasonal variations of ice. And under Greenland, we have a lot of ice. And so we are part of most of what we do is always the ability, it includes the ability to strip away the water, strip away the ice, look under it with a variety of techniques. And the fact that gravity links all of that is an important part of this problem being always multivariate in some sense.
Thank you.
Okay, so any other questions from audience?
You can also write the questions on chat.
And I should mention one thing. I pulled up a website here because Arthur, let's see, you can only see my face, but I'm going to screen share the website here. So Arthur made a live Python site, which is not completely ready, but it's getting there. And oops. And so you can pick parameters of domain size and some subset of the Matern model, and then find some, you know, missing data or do a custom. And then you can, you know, so let me just change your range and then run again, and you'll see everything running. And so there is a live implementation of this method where you see the random field, you see the periodogram, you see the expected periodogram, you see the estimated range parameter for this particular model. And then, you know, you click on France. There's an L missing. And you re-estimate. And, you know, the range is 8.9, but now I'm going to make it, you know, something else, 5.2 run again. It's estimating right now. It's in almost real time, and it comes out as 524 run again. And so there is this play thing here, and France is in here. And there is a little editor by which you can draw, you know, shapes, and then run again. And then you can see interactively what the effect is as I've just cut out a piece or left a piece. So I'm going to put that in the chat. It's a little gimmicky at this point, but we expect that we're going to be able to have time to continually update it and make it even better, because that's really what we want to make sure that we do, that people are using this debias with a likelihood, because it is working so well for us in what we do.
Yeah, that's a very fantastic, very outstanding. Okay, yeah. So I have one question actually. So I wondered for based on your proposed methodology approach, so is there any limitation for the real world satellite data set? So yeah.
Well, so, you know, the answer is always yes, right? So specifically satellite data. Mm-hmm. Yeah. So right now, this here that I'm talking about is a Cartesian framework. Mm-hmm. In my other work, in my prior work, and when we're dealing specifically with satellite data, we are in a spherical framework. So mm-hmm. I have a bunch of other work on spectral estimation that is based in spherical harmonics, because, you know, we must wrap around the Earth. And that's especially important for global satellite missions that are passive observers. So if you think of a satellite, to measure the height of Mount Everest, it will shoot a laser at it and it collects it back. And so that's a point-based measurement. Mm-hmm. But in order to measure things like a magnetic field or a gravity field, that's a completely different measurement. That's a potential field. And so its description is non-local. And so if you, so depending on the satellite mission, it could be very appropriate. Mm-hmm. And when I say this stuff here is very important, it will be like something like point-based direct measurements like ice thickness or the depth of the ocean in some paths or the height of the continent. But when satellite data is much more broad than that, and it includes these non-local diffuse potential fields, and then we will use other methods, especially if the scales are large, so we must go spherical. I see. And that's an open question in the sense that I'd be kind of curious to have, you know, the Matern density and this various bits of implementation mapped into full spherical coordinates. And then in geology and geophysics, people will not even stop there. They'll say, you know, it's really better to go to ellipsoidal harmonics, because where the Earth is, you know, slightly flattened, and in satellite geodesy, the study of the Earth's shape and gravity field, people will take all of that into account, because even at the large scale, some of these small effects are of interest. But in environmental statistics, I know that many of you are on the globe, but the environment is something that I think of as something that is, you know, has a local, a regional, and a global component. And, you know, a Fourier-based, debiased, Cartesian type of likelihood method, like we're proposing here, that's most appropriate for things on a regional scale where the curvature doesn't matter, and when you have limited data, like literally France, or an ocean basin, or a forest in your neighborhood, or something contaminated field, an oil field, you know, where the globe itself doesn't play. But we do have thoughts on that.
I see, makes sense. Thank you very much. Okay, so any more questions?
We have a question on the chat. Mehdi is asking, is the paper out yet? Could we read the draft version?
The paper is in press, and some versions are on archive. So yes and no. but I'm going to give you the archive link while I look it up. So it's coming out in the Journal of the Royal Statistical Society, be in whenever they typeset it, which is soon. And much of the prep work and multivariate, if that's of interest, is in a paper I have with Sophia Ohaid in 2013 in the Geophysical Journal International. But the paper that's coming out is dealing with a lot of things that I talked about today, and that are substantial modifications. Yeah, here it is. I'll send the link. Even what you find on archive now, it's probably only reflecting the second revision of the paper. In fact, I went through 3 revisions and got substantial additions to it. But this thing in the link that I sent is in print just about now.
Thank you.
Okay, so more questions from audience? Okay, so actually I have one more question. That is from the application perspective. So I wonder, so in the spatial domain, your methodology works very well. So I wonder in the future, would you like to extend to the temporal domain? So given a sliding window for the the satellite dataset, so can you also give the estimation for each of them?
Yes, yeah, definitely. And in fact, it's typically how we do it. We either pre-pick a region of interest because we want to know something about something or other in Italy versus France, or we don't know yet. And I think this is an interesting further application is how can we detect domains of stationary behavior within this non-stationary field by a sliding window, and what sort of sliding window would we do? And so then that ultimately, most typically what we do if we don't know the answer yet is that we design a series of growing circles and then just map them everywhere centered on the sphere. And so then we have a sort of, space-time or time frequency or space frequency mapping. And then of course that connects to other things that are still unexplored is wavelet-based methods, which we also have done on the sphere, so there's a lot of open questions here, and it all begins, for me anyway, with an application.
Okay.
So I'm always happy to talk with people about what their specific application is, because it'll require a specific tool. And time series, that's actually the work by Sikulski and Ohaid, that sort of a convergence evolution, because this whole concept of significant correlation contribution and so on, that was introduced there for time series, and it's gotten a lot richer in space than it is for time. But their papers are in Biometrica, and well, they've done that specifically for time series, and they do think about non-stationary as well.
I see, makes sense.
Yeah.
Okay, thank you.
All right.
Okay. So I think, yeah, due to the time limits, so I think, so maybe, yeah, actually I have more questions, but Professor Simons, maybe we can discuss later in person. Okay.
I hope to meet you in person because it's much more fun.
Sure, sure, certainly. All right. So yeah, thanks for the excellent talk today, Professor Simons, and thank you everyone coming and join our webinar today. Thank you very much.
Thank you very much. Thank you.
Thank you. Nice meeting you.
Bye-bye.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Bye.